say qualitative versus quantitative. Observations. Usually when we're thinking about observations, we're talking about measurements here. These measurements can be very qualitative, that is just rough approximations, or they can be very quantitative. Quantitative would be exacting measurements with good precision and good accuracy. And so maybe we should talk about these. But so this is rough. And then when we do quantitative, these are exacting measurements. We try to get it exactly to the correct answer as possible. But what exactly is that? And so exacting, put that in quotation marks. Because whenever we take a measurement, the measurements are usually not exact. There's always, what I mean by exact versus not exact is an exact number has no uncertainty. So let's talk about these. Qualitative measurements will have a great deal more uncertainty than quantitative measurements. But even when you get into measurements, all measurements have uncertainty. Associated with them. Definitions do not have any uncertainty. And so let's take a look at some definitions first. Definitions do not have uncertainty. And so what are some definitions? Well, 1 foot is defined as 12 inches, or 12 inches in a foot. There's no uncertainty there. It's exactly 12 inches in a foot. What other definitions can you think of? Yeah, good. They're 3 feet and 1 yard. That's exact. There's some others, in 1 liter. 1 liter is defined as 1,000 milliliters. That's exact. Most of these, like a dozen. 1 dozen is 12 units. 1 dozen is defined as 12 units. But there's some that are a little bit odd that you wouldn't think are definitions. One of them that's a little bit odd that you might not think is that 1 inch has exactly 2.54 centimeters. And so this is a little bit odd, but they're exactly 2.54 centimeters in an inch. Okay, there's no uncertainty there in an inch. There are other ones that are not exact, and so let's talk about measurements now. When we're dealing with measurements, there is going to be some uncertainty in there. And so, for example, we might say that in 1 kilogram, now there are 2.2 pounds. Okay, is that an exact or is that approximate? Can we say in 1 kilogram they're exactly 2.2 pounds? No. In 1 kilogram, there are approximately 2.20 pounds, or 2.2 pounds. And we can take this a little bit further. And so it's not a definition. This is what we call 2 sig figs. Sig figs just stands for significant figures. And significant figures gives us an idea of a little bit of an idea of uncertainty. And so the sig figs, this gives us an idea about one aspect of uncertainty. I'm going to talk about this in a second, but primarily it gives us an idea of something called precision. When we're thinking about uncertainty, we think in terms of precision, and we think in terms of accuracy. But accuracy and precision, let me talk about that. But it gives us an idea of uncertainty. So when we see a number like that, and it's a measured value, or it could be an estimated. Usually, a quantitative is measure. You use instruments to measure these things. Qualitative, it's just kind of an estimated value used. But if we see this, we go 2.2, and the uncertainty here is not given, but it's usually taken to be, plus or minus, half of the smallest digit. So the smallest is just 0.1. This goes by 0.1 increments. So go 0.1, 0.2, 0.3, 0.4. So there's a tenth. And so half of a tenth is 0.05. And so we say 2.2 plus or minus 0.05 pounds, like that. And so in other words, we have this range, this goes from 2 point, let's see, go from a range of 2.15 to about 2.24. No, it's not exactly plus or minus 0.05, but this is typically the way we'd see this, because if you were to weigh this on something, you guys know about rounding, right? When we round off numbers, we drop the last digit here. So if we were to drop this last digit, this would round to 2.2. And if we were to drop this last digit, it would round to 2.2. And so all the numbers in this range will round to 2.2. And so we say that's it. And so we have a little bit of uncertainty. There's a little bit of range of values. Now, if the range of values is very wide, we call that low precision. It can be all over the place, this wide range. If the range of values is narrow, we call that high precision. And so the higher the precision, the more narrower you can get that range of values. And the lower the precision, the more scattered things are. And so precision is how tight the range is. And so here, we can do this. This is to 2 sig figs, this example. Let's do this example. I know I can get better precision than that. In fact, 1 kilogram is equivalent to 2.20 pounds. Now this is represented to 3 sig figs. 3 sig figs, it's going to really narrow down the range, because when I think about this, I'm thinking now it's going to vary from 2.195 to about 2.204 pounds. And so rather than going from 2.15 to 2.24, I'm going from 2.195 to 2.204. And so you see what's happening here is this is much wider range. This is a much narrower range. And so what's happening to the precision? Which of these two has a higher precision? This one. This is a higher precision. Therefore, there's less uncertainty there. The range has been narrowed. This is a wider range and lower precision. Now, if I go to 4 sig figs, what is it? And so, I don't have it memorized, the 4 sig figs. I need to look that up, but we can easily look that up. I haven't memorized the 3 sig figs, which should be adequate, but some of these you don't really have to memorize. For example, this one is usually given. You know. And so we don't necessarily memorize it. It doesn't hurt to memorize this because it's easy to memorize, but it's normally given. The ones you memorize are these, you know, these English conversions. You got to memorize those. But this one you have to memorize. This one's not necessary to memorize, but it's not difficult to memorize either. I usually memorize it to 4 sig figs, but I memorize it to 4 sig figs by a different way. The way I memorize it to 4 sig figs is what am I doing? I'm doing kilogram per pound. Okay, here I have a choice, although let me just show you so many ads on this site. 2.2 pounds. That's just two. How many sig figs is that? Actually, we count this as significant. This would be considered 2 sig figs. But 2 sig figs is not good because, you know, 2 sig figs is starting to get too qualitative. We want to be much more quantitative. So the more quantitative we are, the more sig figs put in there. And so I'm going to change this. Let's see if that's better there. That works. Okay. So now, how many sig figs is this? This is 4 sig figs. So this is going to be more precise. And so it depends on so out of all these, I'd like to use this one. This is better because it has less uncertainty. But the thing is, how many sig figs can I go to? You know, actually, I can get even better. This particular site, it's 2.205, which really narrows down the uncertainty quite a lot. But let's take a look at this in a more exacting. I don't want a calculator. I just want to, how many pounds? Let's do how many pounds in 1 kilogram. So let's take a look at this. So here, how many sig figs are in this one? Well, we could just count. We just count the digits: 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. And so this one would be the most precise one. It actually goes on. There's more than 9. You know, so this is like pi. Usually, when you use pi, how many digits do you use? 3.14 because 3 digits are easy to memorize, but how many digits are in pi? You know, I think there's a world record. I think somebody memorized pi to 100,000 digits or something like that. Or have you heard that? Something like that. It's a crazy number of digits. Well, of course, this one's much more precise, right? This one's way more precise, so we should use this. We should use this. And you would use this if all your measurements equally as precise. But what tends to happen is that some measurements you can't get this kind of precision. Some measurements are a lot less precise. And so do we have to go crazy on the precision of one if another measurement is really rough? No, it doesn't make sense to in terms of how we do this. And so it's a balance, you know. If everything's super precise, then you be super precise. If there are some things that aren't as precise, then you just be a little bit more precise. And so normally when we have a number like this, we look at the other number. The other number is tricky, because let me ask you this. So typically we look at the other number, but you're going to be asking what is the other number that we're looking at? Well, the other number might be like this. You know, how many sig figs in this? One sig fig. You look at it and you go, that's one sig fig. And then you'd say this. The way we read this is when there's uncertainty, we just say approximate. So in approximately 1 kilogram, there's approximately 2.2 pounds. So would you say this? If somebody asked you, you know, you might say, okay, over here we have 1 sig fig. So in approximately 1 dozen, there's approximately 12 units. In approximately 1 dozen, there's approximately 12 units. Is there uncertainty in both? No, we read this one differently. We say in exactly 1 dozen, there's exactly 12 units. The same thing happens here, you know, with exact. This is, you know, when the number is exact, then what we say is it has infinite sig figs. It's an exact number. And the same thing here. This is infinite sig figs, so an exactly. Well, the way we want to do this is this. We don't want uncertainty in both terms. And so what we'll say is in exactly 1 kilogram, there's approximately 2.2 pounds. And so in exactly 1 kilogram, there's approximately 2.2 pounds, which tells me how many sig figs are in 1. Infinite. This would be infinite sig figs. And I'm going to abbreviate sig figs SF, infinite sig figs. And then this would be 2 sig figs. We know it. Well, it's not exactly 2.2 pounds, you know, it's 2.204622262 9 sig figs. You know, we could keep going. If we wanted to keep going, we'd keep going on here. We aren't. And so that's not exact. So what we do is we don't make both terms approximate. We put all the uncertainty into one term. You know? And so that makes it easier to deal with. And so typically we'll want to know this to 3 or 4 sig figs. The problem is this. You know, we always have this potential domino effect in rounding. You know, whenever we round off a number, we're introducing uncertainty. You know, whenever we round it, so for example, if you were to round this, what would this round to? 2.21. But if I do this to 3 sig figs, what is it? 2.20. Because if I do it to 3 sig figs, I'm dropping a 4. But if I do it to 4 sig figs and then drop 1 to go to 3 sig figs, then I'm doing what's called the double round off. Double round off is a domino effect. And you're only allowed to do 1 rounding. And so really, if I wanted this to 3 sig figs, I'd have to look at the longer number and drop it here, 2.20. Because I don't want to do this domino. The domino would be 6 would bump this up to 3, that would bump that down to 2, this would bump it up to 5, which would bump this up to 1. You see that? You know, we could have so many rounding steps in here, but we don't. Whenever we do rounding, we just do 1 time. We don't do multiple rounding. Otherwise, that screws up our certainty in the number or introduces more uncertainty. uncertainty. So each rounding step leads to what's called a round-off error, which is the uncertainty.
So ideally, how many sig figs?
3 or 4.
3 or 4.
Yeah. Most of the numbers we're going to use 3 or 4 sig figs. We'll never, unless we're forced to, we'll never use 1 or 2. We could use more, of course. More, there's no penalty. In fact, using more is better. But it depends on what you're given. So, let's say how many sig figs we use depends on what we're given. So let's say, for example, 0.5 kilograms equals question mark pounds. How many sig figs am I given? Now this 0, should I count that? So it's 1, 2. No, I don't count that 0. This turns out to be only 1 sig fig. This 0 is what we call a placeholder. In fact, all zeros preceding the non-zero are placeholders. And so let's do an aside. 0.05. If I had 0.05 kilograms, how many sig figs is that? It's still 1 because the 0.0 is not significant because we're going to start writing numbers in scientific notation because pretty soon it becomes inconvenient. So in scientific notation, this would be 5 times 10 to the what is this? 5 times 10 to the negative 1, 2. One way of remembering this is this. This is called the number here. This is called the coefficient. So going from the number or the decimal form to the coefficient, you make this bigger. If we make this bigger, then the exponent has to be smaller. So this gets bigger, this gets smaller. And so this would be the same thing. This would be 1 sig fig. And both of these are the same number. So these are placeholders for the decimal point. And so these are not significant. What if the 0 occurs after? And so if I go 0.50 kilograms, how many sig figs is that? There's 2 sig figs. This is significant. And so in scientific notation, we would record this as 5.0 times 10 to the minus 1. It would be equivalent to 5.0 times 10 to the minus 1 kilograms. Normally a measurement will have the number plus the unit. Do not forget the units here. A lot of people get lazy and they don't, it's too much work to write kg. Or they forget to write kg. It's not good because it's half the credit. Equals how many pounds? And so what we do is, if we want to do this calculation, we could do this setting it up. We use dimensional analysis for the setup. And so if we have 0.5 kilograms like this, then what we want to do is we want to use at least 1 more sig fig. And so for this, we want to use 2 sig figs. So this is 1 sig fig, 2 plus sig figs here. And so in this case, 2 plus would be fine. This would be 2.2 pounds per kilogram. And so I set up an equation like this. Because I know that in every 1 kilogram, I don't have to write 1 here, but for every 1 kilogram, there are 2.2 pounds. And so this is called dimensional analysis because units are also called dimensions. And when we analyze the units, this is why it's so important to write the units again. The kilograms cancels out and leaves us with pounds. And so 2 plus sig figs is adequate there. And so I get 1.1 pounds. 1.1 pounds is, there's rules for sig figs. And so if I do multiplication or division, I have to, this is too much certainty here. This is not taking into account the uncertainty here because if I have 0.5 kilograms, that's anywhere from 0.46 up to 0.54. Quite a big range. When I look at this is a very narrow range, and so I'm not allowed to go from a big range to a narrow range, I have to retain that wide range. And so what I need to do is I need to round this to 1 sig fig. And so one thing you always want to get in the habit of is to show the rounding step. Show rounding step. Always. Always show the rounding step. And so our final answer is only allowed 1 sig fig. 1 sig fig to maintain that same degree of uncertainty that we started. Since we started off with kind of a big range and quite a bit of uncertainty, we've got to end with that.
So do we always use the least sig fig?
No. We don't. That's pretty much the least. However, if you have something like this, we use 1 extra here in this term. This ratio here is what we call the conversion factor. Called the conversion factor. Thing is, would it be okay to use 9 sig figs? Should we go ahead and use all 9 sig figs there? Got it, so why not? Why not use 9 sig figs here? Why we don't use 9 sig figs here is it's not necessary. If we use 9 sig figs and we have to round it to this, it's not going to make any difference. And so in other words, you have a pretty big uncertainty in this number. And then if we use 9 sig figs, it's super precise, what we call a very narrow range. But our final answer, we're only allowed big uncertainty. Right? And so it boils down to it's kind of a waste of time to use 9 sig figs because we're going to get the same answer. Okay, then if I don't use 9 sig figs, let me use 8 sig figs. If I use 8 sig figs, waste. 7, waste. 6, waste. 5, well, kind of a waste. 4, I'll probably get a little bit better answer. Probably the exact same answer. 3, 2, 1. And so what happens is this. If I use 1 extra sig fig here, then it's better, a lot better. If I use 3 sig figs, it's better, but not a lot better. It's just a little bit better. If I use 4 sig figs, then pretty much no change. And so what I do is I just go, okay, in other words, this would be plus 1 or 2 sig figs over given. This is what we call the given. The given, you don't choose it. This is given to you. This one, we choose it. I could use 9 if I wanted. You choose it, so you got to choose the right number of sig figs to use. Now, if I have this one, 0.50 kilograms, how many sig figs should I have in my conversion factor? The conversion factor is just a ratio that's going to convert from one unit to another unit. So, in my 1 kilogram, how many pounds? Okay, now I look at how many sig figs am I given? I have no choice over this. How many sig figs am I given? I'm given 2 sig figs. So given 2 sig figs, then I need to use at least 3. And so if I use at least 3, that's going to be 2.20 pounds. If I use 4, it's a little bit better. If I use 5, it's no better than 4. You know, and what happens is it just tops out at a certain point. And so, but I can express my answer differently now. And my answer, okay, at least in your answer you should write more than what you're allowed. And so I have 2 sig figs that are given. I'm using 3 sig figs here. And so my final answer should have about 2 sig figs of precision. And so my final answer is going to be 1.10 pounds. Okay, then I rounded. Well, I'm only allowed 2. I have 3 here, so I'm going to round it to 1.1 pounds. This 0 is significant. It's not a placeholder. So the zeros in front of the first non-zero are placeholder. The zeros after any non-zero are significant. And so this is 3 sig figs, but I'm not allowed that much precision. I'm only allowed 2 sig figs worth of precision. This is 2 sig figs worth of precision, so I need to show the rounding. Show rounding. That's what we did. So we could do some more of these. How many sig figs is this? 4. That's good. It's 4 sig figs. So we're going to go from kilograms to, let's go from kilograms to ounces. These would be not volume ounces, but weight ounces or mass ounces. And so let's go ahead and do this. The way we do this is we just try to string together conversion factors that we know. So one thing I know is, okay, this one, I'm going to write this in scientific notation. Can you write that one? Tell me how I would write it in scientific notation, because sometimes writing all these zeros becomes a hassle. Uh-huh.
5.05 times 10 to the negative 3.
Okay, close. 5.05 times 10 to the negative 3. This, to me, doesn't work out, because how many sig figs are there?
450.
Yeah, this is only 3 sig figs, so it's got to be 5.050 to retain the 4 sig figs. So you know, in a calculator, we'd never punch that last 0. In a calculator, I'd just punch in 5.05. I wouldn't bother punching in 5.050 because for a calculator, calculator doesn't care about sig figs. The calculator is not keeping track of those things. And then what are we missing? Are we missing anything? Kilograms. All right, now I don't know the strategy. Sometimes you don't know the strategies. So this is the strategy of dimensional analysis. The strategy of dimensional analysis is to figure out a ratio. We need to take kilograms to something else. So I know one. I know kilograms to pounds. And so I have 4 sig figs here, so how many sig figs do I need? Okay, I need 5, but minimum 4. Ideally, 5 plus. Well, it's okay because we got 5 here, so let's go ahead and use 5. How would I take that number and round it to 5 sig figs? It would be 2.2046 pounds. Now, some people like to go the opposite way. Some people like to keep this simple. So rather than saying 2.2, they're, to me, exceptionally lazy. They say there's 2 pounds per kilogram. You know, that's just being lazy. And so they'll round this conversion to 1 sig fig. You know, for me, that's so bizarre. Because why go through the hassle of measuring something this precisely, only to screw it up by doing this? 2 pounds per kilogram. Because maybe they heard that before, 2 pounds per kilogram. Well, you know, if they're like this, then if they say 2 pounds per kilogram, I'd like to sell them some gold. You know, if I sell them some gold, let's say they want a pound of gold, I'll just give them, well, a pound is the same thing as 2 kilograms. I'll just give you 2 kilograms worth of gold rather than the pound. But, you know, are they going to be happy? No, because they're going to get 10% less gold, you know, by doing that. I would be happy because that would be 10% instant profit. And so, don't do that. You know, in fact, it's very unusual to use 1 sig fig. You know, that's extreme. 1 sig fig means uncertainties like this. So rather than, okay, 2 pounds, I'm going to give you your 2 pounds of gold. I'm going to give them 1.6 pounds. I'm going to give them 1.6 pounds and say, hey, that's 2 pounds of gold, right? Because 1.6 rounds to 2 pounds. So not only do I get that 10%, I'm going to get an extra 40%. So they're going to lose 60%. Or is that 60%? 50%. No, less than that. Whatever. They're just going to end up. You want to do that to yourself? No. Let's say you're earning interest. The amount of interest you're earning is, let's say, 1.1 times 10 to the minus 1% interest. You know, I think that's. Actually, maybe this is the current interest rate. 1.1 times 10 to the minus 2%. Let's say you're earning interest, you got a savings account. Do you want the bank to round that? You know, the bank's going to say, okay, I'm just going to call that 1. It's close enough to 1%. You know, would you want the bank to round it like that? No. Oh, because you're going to come out short. That's called round off error. You don't introduce round off error like this. This is a dramatic round off error. Somebody rounds this to 2, huge round off error. You can end up with a lot less gold. Okay? And so be careful about that. Well, this doesn't take us to ounces, but you know, this is it. This dimensional analysis is one of the most important problem-solving techniques in chemistry. It's the way we solve a lot of problems. Is we want to relate things to other things. And the dimensional analysis, the way I like to think about dimensional analysis is it's like, you're walking through a forest or a jungle. You know, you kind of know where you want to go, but you don't know exactly which path to take through it. And so we just explore different paths until we find the path that takes us to the destination. And so oftentimes, unless you've done them before, you don't have any strategy. You know, we just try different paths. One path takes us to pounds. And then we look, can we go from pounds to something else? Yeah. Actually, you should know we could go from pounds to ounces because by definition, how many ounces are in a pound? 16 ounces in a pound. And so here we have 4 sig figs. Here we have 5 sig figs. And here we have how many sig figs? 2 sig figs? This is actually infinite sig figs. There's no uncertainty. It's exactly 16 ounces, no more, no less. And so when I look at the units, it's called dimensions because the dimensions are the units here. The pounds cancel out, and that leaves us with the correct dimension, ounces here. Okay, once I have the dimensions worked out, then I do the numbers. For the numbers, I would just punch it out in the calculator. Let's go ahead and do that. Just gonna get a calculator here. I'll show you. All right, so I have a calculator here, and the way I would punch this out, and your calculators are all different. So I would do 5.05, because this 0 is not going to make any difference on the calculator. I'm not going to put it in to save time. And then I need to do scientific notation. Now, different calculators have different keys for scientific notation. For example, let me just show you the Casio. This is the calculator I use. It's the Casio FX115 Plus. So on this Casio FX115 Plus, oops, that's not the greatest resolution here, but I have this key here that does scientific notation. It's times 10 raised to the x power, so I just plug in x. I hit this key, plug in my x. Now the order I plug in my x varies calculator to calculator. Some calculators will, you'll just plug it in the order. So on my Casio, I type in 5.05, and then I hit the times 10 key, and then I type in -3, -3. And so it'd be like this. Oops. 5.05 times 10 to the minus keys here, -3. Other calculators, you have to do the minus after the number. Like the TI. The one calculator that's very common is the TI X, 10X or something like that, which is different, the key in. This is like the TI. And so rather than having the times 10, I have to hit this one, the EXP key. So if I hit the EXP key, and then I type in, actually this one I'm going to type in like I would normally, not 3 minus, but -3. Let me see if that worked. And so this is 5.05 times 10 minus 3. Let's check it. Yep, it worked. All right, times 2.2046, 2.2046 times 16. And then hit my equals. So I got 1.78, or not 1.178. I got 0.178 Okay, how many digits? Well, normally I write more than I'm given. So if I have 4 sig figs, how many digits should I write? Should I write all of them? No, because I gotta round them off anyway. So if I have 4 sig figs, I'm gonna write 5 sig figs here, 1.17813. Do not round. 5 sig figs. It's because it's 4 plus 1. 4 plus 1 gives me 5. Do not round. Remember about the domino effect. Even if I'm allowed to round this, let's say this digit here, rather than being 1, let's say this digit were 9. Even if this digit were 9, I'm not going to round it. I'm just going to drop it. The reason is I don't want a domino, like what happened with 2.204 versus 2.205. I'm going to get a domino effect. I don't want that. And so even if this were 9, I'm just going to ignore it because I'm only allowed one rounding step. And so this would be ounces. Ounces here. And so this is going to be 0.1781 ounces to 4 sig figs. And so here I have 4 sig figs of uncertainty. There I'm going to have 4 sig figs of uncertainty, and therefore it's good. We're consistent. And so our answer matches uncertainty given. Now, does that sound about right? Remember when we were doing the ppm, ppb? Remember that? This next example, 5.050 times 10 to the minus 3 kilograms. That's equal to 0.005050 kilograms. And so we can do this trick with messing around with the decimals. Are you familiar with the metric prefixes? The metric prefixes are like this. We have kilo. Kilo's typically thought of as 1,000, right? Or 10 to the third, 1,000. Then we have something called mega. Mega would be a million, actually. 10 to the 6th is a mega, a million. You know, I got one of these Bluetooth things from Verizon. They said once you hit 15 gigabytes, because I'm on the unlimited plan, once you hit 15 gigabytes on that, they slow it down to 3G speeds. So I thought, okay. I was talking to the guy, he said, 3G versus 4G, you'll barely notice the difference. And then I hit 15 gigs, and then it got slowed down, but you know, he rather than 3G, it said it got slowed down to 600 kilobytes per second. So it went from 4G. 4G was like 60 megs. I think it was like 60 megs per second, something like that. And then down to 60 kilobytes per second. So they go from 60 megs to 60 kilobytes. Was it 60? Yeah, it was like something like 60 or 600. Maybe it was 600. I remember the old telephone modem days, you know, when you had a high-speed modem. A high-speed modem was like 950 kilobytes. You know, it's enough to check your email, make sure there's nothing other than text in there. But Anyway, kilo to mega to what? What comes after mega? Like, you know, it used to be floppy disks were like 600 kilobytes, 750 kilobytes per disk. And then they had these high capacity floppy disks at 1.4 megabytes. But after mega comes what? Giga. Giga is 10 to the 9th or a billion. But now you go into the store, you could buy terabyte drives, or, you know, computers. Are there any computers that are operating at terahertz? For sure at gigahertz, you know, to whatever. I think gigahertz, are they operating gigahertz? Well, anyway, tera is a billion. Oh, actually, no, not a billion. Gig is a billion. That means tera's got to be a trillion. And then we go the opposite way. If we go to 10 to the minus 2, which is a little odd, this is a centi, which would be 1/100. 10 to the minus 3, which would be 1/1000, would be a milli. 10 to the minus 6 would be a micro. 10 to the minus 9 would be a nano. 10 to the minus 12 would be a someone know? This one you should know because it's an important one. It's a pico. Well, why is a pico important? These are all prefixes. Why is a pico important? Yeah, because of the radius of atoms. Actually, think in terms of diameter. If we think in terms of diameter, an atom's diameter is around, let's say, well, if it's helium, it's around 60 picometers. Hydrogen's around 100 picometers. And so we say atoms on the small side are about 100 picometers. On the large side, several hundred picometers. And so atoms range from 100 to several hundred or more picometers in diameter. What is a picometer? We'll talk about that, but let's give some symbols for it. Tera is just a capital T. Giga is G. Mega is a M. Kilo is a capital M. Kilo is a lowercase k. Centi is a lowercase c. Milli is a lowercase m. Micro is the Greek symbol micro. Do you know the Greek symbol micro? Looks like this. It has a U with tails on both sides. A nano is a lowercase n. A pico is a lowercase p. So these are. And so, I mean, we could do different things. For example, this would be equivalent to, let's move this 3 over. Move this 3 over. We've gone from a kilo to a regular unit. In fact, this would be 5.050 grams. If we move it 3 over again, this would be 5,050 milligrams. If we move it another 3, this would be 5,050,000 micrograms. If we move it another 3 over, this would be equivalent to 5,050,000 what? Nanograms. And this would be 5,050,000 picograms. So if I had, let's say 5.0 0.050 grams, that's equivalent to, what is this, 1,000, million, billion, trillion, 5 trillion, 50 billion picograms are in there. One way to get a feel for this is, for example, a dollar bill. Do you know about how many grams a dollar bill weighs, approximately? A dollar bill weighs approximately 1 gram. Not exactly, of course, but approximately 1 gram. If you take that dollar bill and chop it up into 1,000 pieces, equal size, each piece would weigh. If you take that dollar bill and chop it up into 1,000 pieces, each piece would weigh 1 milligram. Yeah. If you take that same dollar bill and chop it up into not 1,000 pieces, but 1,000,000 pieces, then each piece would weigh a microgram. And if you take that dollar bill and chop it up into 1,000,000,000 pieces, each piece would weigh a nanogram. Or if you chop it up into a trillion pieces, each piece would weigh a picogram. So we do the same thing with a meter. If you have a meter, that's 1 meter, which is about a yard. Is a meter stick. So if we have a meter and we chop it up into how many pieces? If you take that 1 meter and chop it up into a trillion pieces, then each piece would be a picometer. And if you have 100 of those picometers, that's about as big of as an atom. So that's how big the atoms are. I mean, if you could write 1 trillion lines on here, would you be able to see it? No. I mean, would you even be able to count it? If you start from here and then go all the way to here, and there's 1 trillion lines. Could you count each line? You could, but you'd be wasting a lot of time. How long would that take to count 1 trillion lines? Would you be dead? Well, this is, in science, we're interested in questions like this, and these are questions that can be answered easily using dimensional analysis with some, not necessarily quantitative, but some more qualitative conversion factors. So let's say we need to count 1 trillion lines. One trillion, we could either write in decimal form, or we could write in scientific notation. Now the sig figs gets complicated here because what's happening with the sig figs over here? Are my sig figs increasing? The answer is my sig figs stay the same here. And that means these extra zeros, yeah, they're supposed to count. And there we have what's called a rule. Now, a rule's the same as laws. What's the difference between a rule and a law? You guys reviewed the notes. If I gave you a question on the test in a few weeks, what's the difference between a rule and a law? Would you be able to answer? In other words, what you should be doing, is you should be reviewing on a daily basis. So you talk about rules and laws. You don't want to cram it the night before the test. You go back through your notes or whatever else. Do you have it? Well, one thing is, you might not even have it written in your notes. If you don't even have it written in your notes, then just write it off or take the best guess. What would your best guess be?
Just working, how long it would take?
All right. Well, we'll hold that number and we'll come back to it. So, thanks. So if a question like that came up on the test, one, a proportion of you will have forgotten it. Two, a proportion of you will have had it written down but never reviewed it. Only saw it once, wrote it down, didn't remember. Or three, you saw it and you reviewed it a number of times. Hopefully not just once before the final, but a number of times so that it sinks in your longer term memory. Did you have it?
Well, a lot more concrete, or a lot more subject change, stuff like that. I don't know.
Yeah, along those
More
lines.
concrete.
Yeah. So that's in your own words, that's good. Some of these things you want to say in your own words versus what I said. Does anybody remember what I said about the difference between a rule and a law? But I said something else in addition to it. Uh-huh.
The weight of law is heavier than the weight of the rule.
Those are all true, but I said something else, I think. And that is, basically, rules are subject to more exceptions. For example, and I'm not sure if I gave this as an example, but I give this as an example in Chem 1A. The laws of thermodynamics? Do the laws of thermodynamics have a lot of exceptions? One of the laws of thermodynamics, leads one to the conclusion that you cannot build a perpetual motion machine. Have you ever heard of a perpetual motion machine? Many people have claimed to have made a perpetual motion machine, this machine that goes on without losing any energy. It's in perpetual motion. Like a clock, a clock that doesn't have to be wound up. That would be a perpetual motion machine. You can imagine having a mechanical clock you would never have to wind up. You'd never have to put a battery in. They have clocks that you never have to wind up. But those clocks convert kinetic energy because they're on your arm. They convert kinetic energy into potential energy. It's stored in there. So, however, if you have one of those watches that you don't have to wind up and you just let it sit, eventually it's going to run out of energy, and what's going to happen is going to stop. But if you had a perpetual motion machine, it'd never stop. It's like a car, A car you'd never have to add fuel to because it's perpetual motion machine. It's going to kind of stop. Just get it going. Right? There's lots of people who claim to have made a perpetual motion machine, but they haven't. In fact, the laws of thermodynamics, no one, although people have tried, no one has been able to find a violation or an exception to the laws of thermodynamics. But rules are not the same as laws. Rules, there are exceptions to. Are sig figs, are they called the laws of sig figs or the rules of sig figs? They're called the rules of sig figs because there are lots of exceptions. And so that's okay, we just deal with those exceptions. So this is one of them. So this is a bit ambiguous. This is 4 sig figs. But it could also be 3. This could be 3 or 4 sig figs. We know it's 4 sig figs because we know the number it came from. But if you were just given this number, you wouldn't know. The same thing with this. How many sig figs is this? This could be 3 or 7 sig figs. It depends on how or where that number came from. We don't know. We need a little bit of information beforehand. This could be 3 or 10 sig figs. And this could be 3 or 15 sig figs. It has to do with the zeros. Are the zeros placeholders or the zeros not placeholders? And so this is how we'd write this. If we were to write this to 3 sig figs, we'd write it 5.05. I should say 2. I shouldn't say or. I should say 3, 2, 15, 2, because I know the real answer. If this were 3 sig figs, I'd write it 5.05 times 10 to the. Now, if I make this number smaller, I got to make the exponent larger. And so it's not going to be negative, it's going to be positive. So this is going to be positive 3, 6, 9, 12, plus 12. This is picograms, so picograms. That's to 3 sig figs. If I want to write this to 4 sig figs, I'd write it 5.050 times 10 to the plus 12 picograms. If I want to write it to 15 sig figs, this would get rid of the ambiguity. I'd write it 5.05000, that's 6, 0, 0, 0, that's 9, 0, 0, 0, that's 12, 13, 14, 15, times 10 to the plus 12 picograms. This gets rid of the ambiguity. For sure we'd have it. Does that make sense? So when the zeros follow the non-zero and precede the decimal, then if there's a decimal point, then we're good. If somebody put a decimal point here, like this, then we know it's 15 sig figs. If there's a decimal point, we can figure out. If there's no decimal point, then these could be placeholders or they could be actual measurements. All right, let's take a break here, and we'll start up again.